Okay, so thank you for inviting me here. Today we are going to be talking about extending Shellings, which is based upon a result from a 2020 REU that uh, I co-mentored with Anton Dochtermann at Texas State, and Mikhail Coleman and Nathan Geist were the students. So let us start with the basics. The main object that we are going to be dealing with are simplicial complexes. So what are simplicial complexes? It's just a collection of sets that satisfy, well, it's hidden here, but whenever you have a set inside your collection, that subset of that set has to be contained in the collection as well. Then we call the maximal elements, the inclusion Y maximal elements you have are called the facets. And the dimension of the dimension of the complex is going to be the largest size of the maximal element minus 1. And moreover, we say that the simplicial complex is pure if all the facets have the same cardinality. So simplicial complexes appear everywhere. They appear in combinatorics, topology, and also in algebra as well by looking at something called the Stanley reason array. So the notation that we are going to be using a lot is, since given a simplicial complex, just from this definition over here, if you can encode all the facets, then you basically have all the information of all the faces because they're just going to be the subsets of the facets. So we are going to be using this notation of a simplicial complex being generated by a set of facets. So what this means is that the facets are going to be 1, 2, 3, and 4, 5, 6, the largest sets. And your simplicial complex is simply going to be the collection of all the subsets of those guys. So everything from the empty set to the facets themselves as well. So this is an example of a pure simplicial complex because the two facets have the same size. And moreover, dimension is going to be 2 because the dimension is the size of the set minus 1. So that's what a simplicial complex is. Now, not just a simplicial complex, but we are going to be dealing with a special case of simplicial complexes called shellable complexes. So the intuition behind shellable complexes are the ones that are very nicely peelable. For example, if you have a pizza, then you can peel off the slices very nicely. Or for example, if you have an orange, then you can constantly peel off the slices very nicely there as well. So you can think of shellable complexes as ones that are very nicely peelable. And here's the formal definition. Given a pure d-dimensional simplicial complex, so again, the facets are going to be size d plus 1 sets. We say that the complex is shellable if there exists an ordering of the facets such that this nice intersection condition holds. So whatever for the previous chunk you have, for the previous chunk, when you're attaching a new facet to that, the intersection has to look nice, mostly of pure of dimension d minus 1. So let's look at an example. This is a Schelling ordering because the ordering we have on the facets, F1, F2, F3, F4, and F5, that turns out to be a Schelling order. Why? Because F1, well, that's good by itself. If you attach F2 to what you have before, that is F1, then the intersection is just going to be a single edge over here, which satisfies this condition that it's pure of 1 less dimension. And when you try to attach F3, compared to F1 and F2, the intersection of F3 with it is, again, a single edge, so that looks good. And F4 attached to F1, F2, and F3, again, the intersection is a single edge, so that's good. And now for F5, when you attach it over here, again, the intersection is a single edge, so that's good. So this is a Schelling ordering. And since this complex has this nice ordering of the facets that is a Schelling ordering, we call it a Shellable complex. On the other hand, if we look at the following ordering of the facets F1, F2, F3, F4, and F5, this is in fact not a Schelling order. Why is that? Actually, up until F4, it's good. But when we try to attach F5 to F1, F2, F3, and F4, what happens is that the intersection consists of this vertex at the top and this edge over here. So this vertex and this edge is the intersection of F5 with the previous part. And what happens is that this is not pure because this is a facet. This is an inclusion-wise maximal face. And this is also an inclusion-wise maximal face in the intersection, but this has dimension one, this has dimension 0, this has dimension 1, dimension doesn't match. So intersection looks bad, and hence therefore this is not a Schelling order. So again, a Schelling order is basically, can you attach a new facet to the previous guy so that the intersection looks nice? Yes. The question is, do we want the intersection to be Shellable? That's a good question. Let's see. We definitely want it to be connected. So it is, the intersection is pure of dimension d minus 1. The question is, does it have to be Shellable? I'll have to think about I'll have to think about it. Does anyone perhaps know the answer? Yes. Right, so we don't require that the intersection is Shellable. But the question is, if you have a Shellable ordering, can you find an ordering such that it satisfies an extra constraint? And I'm not sure. I'll have to think about it. Yeah. Okay, yes. Sorry, let's move on. So here's a different language to think about Shellability, which I like to use. So another way to think about Shellable complex is the following. Do you have an ordering of the facets such that for any pair of facets, you can find a chain of adjacent facets in between using the smaller facets? So this chain of adjacent facets, let me explain what that means. So two facets are said to be adjacent if their intersection is a codimension 1. So for example, F5 and F4 are adjacent, F3 and F4 are adjacent, F2 and F3 are adjacent, and so on. So in this picture, F1 and F5 are not adjacent. So if they had a face, if this was just a single edge, then they would be adjacent. Oh, if you join these two together? But even then, their intersection. Okay. So what happens if you add this edge? That's your question, right? Yeah, intersection is not going to be pure in that case because you still have this facet. So we say that, so this, by the way, this is called a gallery via the result by Vic Rayner and his students. So if you have a chain of adjacent facets such that you only use the facets that are smaller than the bigger of the two facets, and if you have this exchange condition, that is the intersection of the two facets in question have to be contained in each one of them, then we say that this is an alternative definition to Shellable. So let's take a look over here. We have an ordering F2, F1, F2, F3, F4, and F5. Why is this a Schelling order? Because whatever pair you choose, for example, like F2 and F5, you can maintain the intersection, which is this dot in the middle. While maintaining the intersection, you can take the chain of adjacent facets, that is F3 and F4, and get to the other facet. Is that okay? So another way to check whether a complex is Shellable or not is see if your ordering of the facets satisfy this nice gallery connectedness property. So that also helps seeing that this is not Shellable, because if this was Shellable, then you need to have a chain of adjacent facets going from F1 to F5. while maintaining the intersection, which is impossible because all other adjacent facets have to go in this way and they cannot maintain this vertex. So that's another way to see shellability. Any questions for us? Yes, adjacency is basically, is there a codimension one face that they both share? Now, what are some properties of shellability? First of all, it's known that shellable complexes have the homotopy type of a wedge of spheres. So they have very nice looking homology. Like in particular, homology is going to be trivial except for the highest dimension. And if you have a shellable complex, then its associated algebra is very, very nice. And some examples of shellable complexes include boundaries of simplicial polytopes, independent complex of matroids, and moreover, if you have a shellable complex already, and if you pick a dimension threshold, shed off all the faces above that dimension and just take the faces below that dimension, which is, in a more fancy way, you're basically taking the k-dimensional skeleton of that complex. And given a shellable complex, if you take the k-skeleton, that is going to be shellable again. So for example, starting from a simplex, which is obviously shellable because it only has one facet, the k-skeleton of that is actually a uniform matroid. So this is another way to see that the independence complex of uniform matroids is a shellable complex. Of course, it's true for general matroids though. And also checking whether a complex is shellable or not is a very, very, very hard problem because it was recently showed that determining whether a complex is shellable or not is actually NP-complete. And another nice property of a shellability is that H vectors are very interesting statistics, which come from counting the number of faces of each dimension and doing a particular shift. And you can actually obtain the entries of the H vector just by pure counting if you have a shellable complex. So that's very nice. So long story short, shellable complexes are ones that are studied quite often and are considered very nice class of complexes. Now, a natural question to ask, just from the way how shellable complexes are defined, because remember the definition of shellable complex is given a chunk, can you add a new facet so that the intersection is nice? So a very natural question to ask is this notion of extendably shellable. That is, if you have a shelling of a subcomplex, can it be extended to the shelling of your complex? So in other words, can shelling order be obtained in a greedy way? So if you have a shelling of some smaller thing, can you always complete that to a shelling order of your complex? So what is known regarding this extendably shellable is that first, any two-dimensional triangulated spheres is extendably shellable. All rank 3 matroids, that is basically a collection of size 3 sets that satisfy a certain property are extendably shellable. And any D sphere with D plus 3 vertices is extendably shellable. And what you should keep in mind is that extendably shellable sounds nice, but actually for a lot of shellable complexes that people study, this is a property that usually doesn't hold. This usually fails miserably. And it's quite easy to come up with examples. Here's one that is quite small. So this is a shellable complex. It's a pure complex of dimension 2 on 6 vertices. But if you start with this subcomplex, which is shellable, then it is actually impossible to add a facet from this list over here so that it is still shellable. So in general, extendably shellable is a property that fails quite often. So this motivated the following question. Yes. Oh. Why is extendably shellable interesting? So you can find shelling orders in a greedy way not good enough? Because I mean, finding shelling orders is very hard, right? Like we have seen. Yes, because you can just do it greedily. So any partial Schelling order you have been constructing, you never have to backtrack. Very good. Yes. Thank you for the comment. So you never have to backtrack when finding a Schelling order. That would be the dream, actually, because if you, so I did a lot of computation regarding Schelling orders using Sage, and this is very, very slow. And I always dream like, is there some faster method? But if you have an extendably Shellable complex, and you can actually do it very fast, because you don't have to back. It's gonna be definitely harder than deciding whether it is Shellable or not. So the motivation for our work is the following conjecture posed by Simon. So Simon conjectured that this crazy nice property holds for all k-skeleton of a simplex. So what does this mean? So a pure d-dimensional complex is said to be Schelling completable if basically given any Schelling, you can keep adding facets and maintain a total Schelling of a k-skeleton of a simplex. So in other words, if you have a Schelling or if you have a Shellable complex already, can you add a facet and still keep it Shellable? And this conjecture is basically equivalent to this question, just because of the way that extendably Shellable was defined. So this conjecture only seems to deal with these objects, but if you stare at the definition carefully, it actually is a conjecture about all Shellable complexes. So if you have a complex that is Schelling completable, then any Schelling can be completed, well, just from actually this follows from the definition. It's because Schelling again comes from looking at the previous chunk and the new facet, and the ordering you have on the previous chunk don't really matter at all on how the intersection actually looks like. So if you have a Schelling completable complex, then you can actually complete any Schelling order you currently have. So Simon's conjecture says that any pure Shellable complex is Schelling completable. And this conjecture is actually very, very simple when the dimension or the codimension is very, very small. So for example, if you take k equals 0, this is an obvious statement because every complex is in the dimension 0 case is actually Shellable. And similarly, when dimension is 1, what happens is that Shellable complexes, simplicial complexes in dimension 1 are just consist of vertices and edges. And if you just have a simplicial complex consisting of vertices and edges, that is essentially a graph. And given a graph, what is a Shellable complex? It's just when it's connected. So Simon's conjecture in dimension 1 case is basically, if you have a connected graph with some missing edges, can you always add an edge so that it is still connected, which is quite easy to prove. And codimension 1 case, again, is quite simple because in codimension 1 case, every complex is Shellable there. So the first non-trivial cases are dimension 2 and codimension 2 cases. And for the dimension 2 case, this actually follows from the Björner-Eriksson's result on uniform matroids. And for a codimension 2 case, it was already proven, and there is actually a very nice graph theoretic reason why this is true. So long story short, when up until when dimension equals 2 and codimension 2, it's already being done. But starting from the dimension 3 case and codimension 3 case, the conjecture is just like wide open. And what we are going to do is instead of focusing on a particular dimension, we are going to pick a very, very nicely behaved smaller subclass of Shellable complexes and show that they can be extendably Shellable. So here's some examples of Schelling extendability before we actually go on to the hardcore stuff. So a very nice simple case of simplicial complexes is called the shifted complexes. So a shifted complex is when you have an ordering on the vertex set, for example, from 1 up to n, and you have the property that for any face in your complex, if you replace a vertex with a smaller vertex, then it should again be inside your simplicial complex. Then what is known is that if you have a shifted complex, then adding the Reflex smallest missing d+1 subset again results in a shifted complex. So by the way, to help you recall what Reflex is, lexicographic ordering is the usual dictionary order such that you start from the leftmost entry. So you start from the leftmost entry and then start comparing there. And whenever you have a tie, you move to the positions to the right. So for example, we have a tie between 1, 2, and 1, 2, 5 in the first two positions. So we compare at the third position. Reflex is the opposite. Instead of starting at the leftmost position, you first start comparing the rightmost position. So for example, you can see that here we have a chunk of guys ending with 5. Here we have a chunk of guys ending with 4, and here we have one guy ending with 3. So you start comparing from the rightmost entry, and then whenever there is a tie, you move left. That is the Reflex order. Then given a shifted complex, for example, this is a shifted complex because, for example, you have 1, 4, 5, replacing 4 with any of the smaller elements, say 2 or 3, gives you something that is already inside the complex. So 1, 2, 5, 1, 3, 5 are inside the complex. Given a shifted complex, you look at the Reflex minimum missing. So here 2, 4, 5 is actually the smallest that is missing. Then what happens is that if you add that, that is still a shifted complex. So since shifted complexes are known to be shellable, these two results combined basically tell us that shifted complexes are examples where it is extendably shellable. Is that okay? Because you can extend the shifted complex by one facet, and since it's now going to be shifted complex again, it is going to be shellable. And another interesting case is the dimension d on d+3 vertices case. So the main idea here is that we are looking at d+1 size sets inside 1 up to d+3. So it's much more efficient if you look at the complement, because the complements of these sets are going to be just of size 2. So a well-known notion of dual for simplicial complexes is what is called the Alexander dual. Alexander dual, what it does is for each complement of a face, a complement of a non-face, you're going to take that. So here's an example. If you have the simplicial complex 1, 2, 3, 1, 2, 4, 1, 3, 4, 2, 3, 4, 1, 4, 1, 2, 5, which is a pure complex, if you take the Alexander dual, then this is going to be the result. Why do we have 5? Because 1, 2, 3, 4 is not a face. And why do we have 1, 2? It's because 3, 4, 5 is not a facet here. Is that okay? So that's the Alexander dual. Now, the bad thing about this Alexander dual here is that it's not pure anymore. So we want to be focusing on the facets and keep everything pure. But if you just take the Alexander dual, then, well, we have some weird part over here that it would be nice to remove. So what is the thing that people working in this field do quite often to get rid of those annoying parts is if you take the chordal complex of the complex first and then take its Alexander dual. So a chordal complex is basically you look at the facets you have and encode a set of vertices where you basically have a clique. That is, when you have all possible 3 subsets of the given vertex set, then you encode that as a facet of your chordal complex. Like for example, here, 1, 2, 3, 4 is a facet because we have all 3 subsets of 1, 2, 3, 4 inside the original complex. So if you take the chordal complex and then take its Alexander dual, then that is exactly what we want. It's going to be the complement. So it's going to be the complement of each of the set and then taking the complement of that collection. This is what we are going to be calling the dual. And for the d+3 case, what happens is that if you take the dual then each complex basically corresponds to a graph because all the facets each correspond to a cardinality 2 subset. And what happens is that shellable complexes are in bijection with what is called a chordal graphs. The chordal graphs are very nice classes of graphs where whenever you have a cycle, then you're going to have some chords of the cycle contained in your graph as well. So using the fact that in the DD plus 3 case, everything can be encoded in terms of those chordal graphs, that's how these people show that these kind of complexes are Schelling completable. So when codimension is 2, you basically use graph theory. So now, before I introduce what is the nice class of complexes that we are going to be focusing on, we first need the notion of what the link and the deletion of simplicial complexes is. So first of all, deletion is very, very simple. It's deletion of a face is you take all faces that do not directly contain that. So for example, somehow the colors are not being shown, but so this is our original complex. And what happens is that we have the triangle EBC colored in. Again, I don't want to actually color it over here because I don't want to pay for it. So we have the triangle EBC colored in. Oh, okay, that would be great. Well, at least. And we have a hollow tetrahedron here for ABCD, meaning that you have the boundary of the tetrahedron, but not the interior. So ABCD is not a face of your complex. Is that okay? So you have ABC, ACD, ABD, and BCD, but not ABCD. Then how does the deletion look like? Deletion is basically you remove this and then take all the faces that was originally here. So it's going to consist of this triangle EBC and BCD. That's how the deletion of A is going to look. And how does the link of A look like? The link of A, you're basically going to be taking faces away from A, but in a way so that combined with A that gives you the original face of the complex. So for example, all the vertices are going to be in the link because we have the edges AE, AB, AD, and AC. So all the vertices are here. And the edge BD is going to be in the link because we have the face ABD inside the original complex. So we have the edges BD, BC, and BC, each corresponding to the triangles ABD, ABC, and ADC. But in the link, again, it's kind of hard to see from how the colors are messed up. The triangle BCD is not actually contained in the link. And why is that? Because BCD together with A is the entire tetrahedron ABCD, but that's not supposed to be in our complex. So that's why the triangle BCD is actually missing here. Is that okay? It would have been so much better if the colors showed up. But I hope that gives you a rough idea of what the link and the deletion is. So if you already have learned about matroidal deletion and contraction, it's quite similar, but also quite different at the same time. So let me explain. So these two operations are put on our main object, which is our shellable complexes. Link of a shellable complex is again a shellable. It behaves very nicely. But deletion of a shellable complex usually have nothing to do with shellability. An easy example to see is imagine a triangulation of a big polygon on a plane with a lot of interior points. Now, if you just simply delete the dot inside, then you're going to have a one-dimensional hole inside, and therefore it's not going to be shellable anymore. So deletion usually messes up shellability quite badly. And also, deletion doesn't even preserve purity of a complex in general. If you have a simplicial complex that is generated by these two facets, 1, 2, 3, 4, and 5, 6, 7, 8, and now if you take the deletion by 1, then in the new complex, what are the facets? This is still going to be an inclusion-wise maximal set, so that is a facet. And since 1 is being deleted, you now have 2, 3, 4 as a facet inside the new complex. So that is not going to be pure anymore. So in general, deletion behaves quite chaotically for simplicial complexes. So what we want to do is look at a very, very nice small class of Shellable complexes that behaves nicely, not just with respect to the link, but also to the deletion as well. So here's the definition. A simplicial complex is called vertex decomposable if it is either a simplex already, or there contains some vertex that you can decompose by, which is called a Shellings vertex, such that deletion is again vertex decomposable, and the link is again vertex decomposable, and any facet of the deletion is again a facet of the original complex. So you can, as you can see, it's a recursive definition. The deletion and the link are both nice again, and you have some kind of a gluing condition over here. So why is this not something that is obvious is because we saw in the previous slide that if you take the deletion, purity is usually not preserved. But here we are requiring that all the facets of the deletion is again a facet here, so purity, so it's kind of already requiring that purity has to hold. So why was this studied? This was introduced by Provan and Valera in their study of the Hirsch conjecture. And vertex decomposable complexes are indeed Shellable. Now, let me give you another alternative definition that, well, I used when I was dealing with this project, because I dealt with a lot of matroids, and I always felt like for pure simplicial complexes, you only have to take a look at the collection of facets. So here's an alternative definition. So given a collection of facets, let facet deletion be the literal or matroidal deletion. That is, you're taking the facets that do not contain H, and the facet star is going to be you're taking the set of facets that do contain H. So what's happening here is that given a collection of equi-cardinal sets, you're partitioning it into two pieces based on whether it not contains H and whether it contains H. So you're basically partitioning the set of facets. Then having this notion in mind, what is an alternative definition of vertex decomposable? It's when you either have just one facet, or you partition into two pieces. Each of them are vertex decomposable. And what is the interpretation of the gluing condition? Every facet containing the vertex has to be adjacent to some facet non-containing the vertex. So that's why we call this the gluing condition, because it's basically enforcing how the two pieces have to interact with each other. So that's the definition of vertex decomposable. So let me show you some examples. Again, this is the alternative definition, copy and paste it down. And this is the case skeleton of a simplex, because it contains all the three subsets of 1, 2, 3, 4. And now let's see why this is actually vertex decomposable. So 4 here is a decomposing vertex. Why? Because if you split this list of facets into the ones that not contain 4 versus the ones that do contain 4, we have the gluing condition satisfied, because for everything containing 4, each one of them are adjacent to some facet not containing 4. Is that okay? So 1, 2, 4, 1, 3, 4, 2, 3, 4 are all adjacent to 1, 2, 3, and hence the gluing condition is satisfied. And moreover, this just has one facet, so that is vertex decomposable. And now from over here, you again pick a vertex, decompose, and check that that is vertex decomposable. So case skeleton of a simplex is vertex decomposable. The shifted complexes that we have seen earlier, which was a nice example of Schelling completable complexes, is known to be vertex decomposable. And Provan and Bilera also show that all the matroid complexes are vertex decomposable. In particular, you can use any Schelling vertex. So what I want to convey here is that vertex decomposable complexes, the conditions look so much stronger than shellable complexes, in particular because it's enforcing that your complex has to behave nicely with respect to the deletion as well. But it's still a pretty big class in the sense that it contains all the matroids. So it's not some like really super small class. Of course, compared to Shellable, it's much smaller, but still it's pretty big enough. So any questions or comments so far? We are defining that as the base case for our definition. So here we say that a complex is vertex decomposable if it's a simplex, and the simplex is the one that just contains a one facet. So it's pretty much a translation of that. Any other questions or comments? Okay, then finally, here's our main result. So in the 2020 REU, what we proved was the following. Vertex decomposable complexes are indeed Schelling completable. That is, you can keep adding facets that are missing and keep the shellability condition. And what we prove is actually even more. What we show is that vertex decomposable complexes can be extended, keeping it being a vertex decomposable complex. So starting from a vertex decomposable complex, you can add a facet so that it is still a vertex decomposable complex. And since vertex decomposable implies shellability, that implies that it's Schelling completable. And actually, even more, we show that you can do this by coming up. So you can always come up with an ordering on the vertex set. So you can come up with an ordering on the vertex set such that if you take the Reflex smallest with respect to that ordering, then adding that missing facet guarantees you another vertex decomposable complex. So this was motivated from the properties of the shifted complexes, because given a shifted complex, there exists an ordering on the vertex set such that if you plug in the Reflex smallest that's missing, then that is still a shifted. So if you just change it shifted to vertex decomposable, then it still holds. Of course, vertex decomposable is much bigger than shifted complexes. So here's an example. Here's a kind of an ugly looking example. So what is the idea behind finding the ordering of a vertex set so that you can extend by taking the Reflex missing and get a vertex decomposable? Well, here's the algorithm. So if you have a shedding vertex, you always set that to be the biggest vertex. And then now it's like kind of a choose your own adventure. So if you look at the deletion of the vertex, and if that is a uniform matroid, that is, if it's a K-skeleton of a simplex, then we recursively take the decomposing order of the link part. Otherwise, we take the decomposing order of the deletion and then just simply attach the shedding vertex at the end. And that is going to be the ordering of the vertex set that you can use to extend via Reflex. So here's an example. This is a pure three-dimensional simplicial complex on 6 vertices. And it has a shedding vertex 6. Now, if you look at the deletion, then this is full because it is a uniform matroid. You have all 4 subsets of 1 up to 5. So what we do is we instead look at the link. The link is going to be, we are basically looking at all the facets over here that contain 6 and then remove 6 from that. So it's going to be generated by this set of facets. And recursively, what we can check is that this has the decomposing order 1, 2, 3, 4, 5. And if you take the Reflex smallest that is missing, which is 1, 3, 4, then attaching 1, 3, 4 extends this complex to a vertex decomposable complex. So what we can do is carry the result over. So here we attached 1, 3, 4. What we do here is if we attach 1, 3, 4, 6, then that is going to work. And similarly here, we have another case of a vertex decomposable complex. 7 is the vertex that you can decompose by. So if you look at the deletion of that, this time it's not full because it's not a uniform matroid. So, but this complex is actually what we just studied. So it had the decomposing order of 1, 2, 3, 4, 5, 6. And if we take the Reflex minimum, that is 1, 3, 4, 6 that we can extend by, so we can just, again, take the decomposing order 1, 2, 3, 4, 5, 6, 7. And then now the Reflex missing here is same as Reflex missing here, so we can extend by that. So that's the recursion that allows us to find the facet that we can extend by. So again, one thing to be aware is that there exists an ordering of the ground set such that this method works. We are not saying that this works for all orderings of the vertex set. So having that in mind, how do we apply this to matroids? A pure simplicial complex is a matroid if it satisfies this well-known exchange property. And matroids are vertex decomposable. So, and also another nice property of a matroid that is quite well known is that if you pick an arbitrary ordering of the ground set, and then take the lexicographic ordering of the facets, then that is actually a Schelling order. So for matroids, you can get a lot of Schelling orders very, very fast. So what is our result of matroids is that if you have a matroid, then pick any ordering of the ground set. Then now if you take the Reflex smallest that is missing, then you can extend that so that it is vertex decomposable. Of course, it would have been nice if it was a matroid again, but that actually turns to be false. But regardless, if you have a matroid, you can pick any ordering on the ground set, and you can extend that via keeping vertex decomposability. So again, here's an example. So given a matroid, it is not possible to fix an ordering on the ground set and keep adding the Reflex missing facets and eventually complete the Schelling. So here's an example where that miserably fails. Is if you have the following facets, let's try keep adding Reflex minimal that is missing. So starting from a matroid, adding this is actually okay. Adding this is okay, but at some point it fails because once you get to 1, 2, 5, 6, it's very easy to see that it's not even a Shellable complex anymore because given a Shellable complex, the link again has to be Shellable. But if you take the link of this complex of 5, 6, then you're going to get something that is where the facets are not even connected. So there's no path between these two facets, and therefore it's not going to be Shellable. So sadly, given a matroid, you can't just keep adding Reflex and eventually complete the Schelling. You have to change the ordering of the ground set at some point. So this was related to what was briefly mentioned. What is the condition such that given a matroid, you can keep adding the missing correct size set and again get a matroid? There's actually a result by Kahn and Truemper saying that you can only do that if the missing set was a circuit hyperplane. So if you can find a circuit hyperplane in your matroid, then you can safely add that as a new basis and create a new matroid that has one more base. Also, our result gives another proof for the D+3 case, which basically had a nice graph theoretic interpretation. So what we have is that if you're looking at the codimension 2 case, that is D-dimensional Shellable complexes on D+3 vertices, then what happens is that vertex decomposable is actually just exactly same as Shellable for those small codimension cases. So what will happen is that all those different notions, shellable, extendably shellable, Schelling completable, and vertex decomposable, they all just collapse to be the same thing. And this theorem is tight in the sense that if you look at d-dimensional simplicial complexes on d plus 4 vertices, then of course this one miserably fails. There are a lot of shellable complexes that are not vertex decomposable anymore in that case. So what to do afterwards? There's this notion that generalizes vertex decomposable and kind of allows you one to interpolate between vertex decomposable and shellability, and that is the notion of K decomposable. So a simplicial complex is called K decomposable. Again, this is the base case if you have a simplex, or there is a face that you can decompose by with dimension bounded above by K, such that the deletion and the link are recursively again satisfy this property, and that you again have this nice gluing property between these two. So that is the notion of K decomposable. It's probably hard to remember what was there before, but compared to vertex decomposable, the only thing that is different is basically now you're allowing to decompose using non-vertex faces. So in particular, if you plug in K equals 0 and study 0 decomposable, then the only face that is allowed is a dimension 0 face, which is a vertex. So this basically is same as vertex decomposable. Now what's slightly, well actually, and also we get a nice chain of these classes because the bound is an upper bound coming from K. So if it's 0 decomposable, only faces you're allowed to use to decompose are the vertices. But for 1 decomposable, the faces that you're now allowed to use are the vertices and edges. So just from the definition, I hope it's very clear that K decomposable is a subclass of K plus 1 decomposable. Is that okay? So we get this a nice chain of subclasses. Vertex decomposable is same as 0 decomposable. That is contained in 1 decomposables, 2 decomposables, and so on. And it might not be obvious from the definition, but if you try it, it's actually quite simple. Shellable is exactly same as D decomposable for D-dimensional pure simplicial complexes. So K decomposable is indeed a definition that goes between vertex decomposable and shellability. So an obvious question that one should ask is, given a K decomposable complex, can you extend it by one facet at a time while still maintaining it being a K decomposable? So for this question, K equals 0 is exactly our result for vertex decomposable. And if you can somehow answer this question for K equals D, that would be answering Simon's conjecture. So here is some example of a simplicial complex that is not vertex decomposable, but is one vertex decomposable. So over here, if you try to find a decomposing vertex, actually nothing should work. So for example, what would be an easy one to check? Let's see, if I take 1, try to take 1 to be the decomposing vertex, then again, the condition is that everything containing 1 should be adjacent to something not containing 1. But where does it fail? Where does it have? Yes, so given 1, 2, 3, if you delete 1, that is 2, 3, but there's nothing here that contains 2, 3. So 1 is not decomposing, and actually it's the same for 1 up to 6. But if you're allowed to take edges as decomposing faces, then you can decompose quite easily, for example, using 1, 5. So the only facet containing 1, 5 is 1, 2, 5. And well, it's quite easy to see that 1, 2, 5 is adjacent to something outside, for example, 1, 2, 4. So this is an example of a complex that is 1 decomposable, but not 0 decomposable. So the most natural question to ask based upon our result was, if you have a one decomposable complex, can you add a facet and still maintain it being one decomposable? And although I did say work in progress, we tried this during all of summer of 2021 and failed quite miserably. So if you have any good ideas, please let us know. It seems to be a lot harder than zero decomposables. So let me just end with another nice open problem. So a notion that is quite related to shellability is the notion of a rich chordal. So first, where does the notion of a rich chordal come from? It comes from this philosophy. So elaborating a little bit more on the connection between D+3 case and the chordal graphs. So one can actually combinatorially characterize exactly what edges you can remove that corresponds to adding a shellable facet. So the condition is that the edge that you remove has to be contained in a unique maximal clique. So for example, going from here to here, 1, 3 is removable because 1, 3 is contained in a unique maximal clique of 1, 2, 3, 4, 5. And going from here to here, 1, 4 is removable because 1, 4 is contained in a unique maximal clique of 1, 2, 4, 5. So that was why 1, 4 was removable. And similarly, going from here to here, 1, 5 is removable because the unique maximal clique containing it is 1, 2, and 5. Yes. So another way to think about Simon's conjecture is look at this dual picture and try to shed off faces that satisfy a certain condition. So based on that, this notion of rich chordal was defined. So a ridge is a face of codimension 1. So basically, it's what connects the two facets. We say that a ridge is simplicial if it is very dense outside. So what this means is that you take a look at all the facets containing the ridge, look at the supporting set of vertices, and see if that forms a clique. That is, all the possible sets contained within that vertex set is a facet in your complex. So if that is satisfied, that is, if it's really dense, then that is called a clique. So here's an example. This is a simplicial complex of pure of dimension 3. 1, 2, 3 is a simplicial ridge because if you look at the facets containing 1, 2, 3, it's 1, 2, 3, 4, 1, 2, 3, 5. So the vertex set is 1, 2, 3, 4, 5. And for 1, 2, 3, 4, 5, you actually have all the possible subsets of size 4 appearing within that vertex set. Hence, therefore, 1, 2, 3 is a simplicial ridge. On the other hand, 1 to 5 is not a simplicial ridge because the facets containing 1 to 5 are 1, 2, 5, 6, and 1, 2, 4, 5. So the vertex set is 1, 2, 4, 5, 6. And in 1, 2, 4, 5, 6, you do not have all the size 4 subsets that appear. So it's not a simplicial ridge. Then a complex is called rich chordal if it's either empty or you can peel off according to a simplicial ridge. Then Bigdelli and Faridi actually conjectured that, so Alexander dual of a chordal complex, that is basically the correct dual. So if the correct dual is shellable, then the complex is rich chordal. That was their conjecture. This was largely motivated by that relation in DD+3 between shellable complexes and chordal graphs. Now, what is known is that if you replace the word with shellable, then this is true. So if the dual is a vertex decomposable complex, then the complex has to be rich chordal. But Benedetti and Bolognini actually proved that this conjecture is very false. If you replace, so there are 4 decomposable complexes where its dual is not rich chordal. So the obvious question is, we know that this is true if this is replaced with 0 decomposable. And we know that this is false if this is replaced with 4 decomposable. So the obvious question is, well, how about things in the between? Is this true for 1 decomposable, 2 decomposable, and 3 decomposable? And just in case you're wondering, the counterexample they provided over here, that is an example of a 4 decomposable complex where the dual was not ridge-chordal. This turned out to be not 1 decomposable. So the example provided here actually doesn't really help on studying whether this is true or not. So anyway, I feel like that would be another interesting direction to go regarding this problem. Okay, so that's it. I hope you enjoyed it. Sure. If it's Schelling completable, is it vertex decomposable? Yeah. Oh no. Give us a second. Let me just make sure. Okay, I don't have an example right now, but I can pretty much guarantee you that there are a lot of Schelling completable complexes that are not vertex decomposable. Yes. Mm-hmm. Okay. Oh, actually, give me a sec. So, not guarantee. I can 100% certainty say that the converse of this is false. So there are a lot of examples. So there's a paper by some Japanese authors that contains a lot of examples that are not vertex decomposable but are Schelling completable. Yes. Ah, I do not know. It's because usually when you just add the Reflex, I mean, this is based upon experience, not mathematical insight or anything. So according to my experience, given a matroid, if you just pick an arbitrary ordering of the ground set and add the Reflex smallest, it's usually not a matroid anymore because the Reflex smallest set you have chosen is not a circuit hyperplane. So at that point, it's very unlikely that you can keep using that ordering on the ground set. There might be some special classes of matroids where you can fix an ordering of the ground set and keep adding Reflex smallest and eventually reach the K-skeleton of a simplex. But I don't know. Yes, that's the usual.
Possible to go in that order, like maybe add several elements, but you can only.
So when you're Schelling completing a matroid, would it be possible to go through only matroids, even when you add multiple at a time?
Yeah. So you just look at cover in relation.
Oh, that is a really good question. Let me first check if I can actually say anything about it because my reflex response is that I don't know, but I don't know. because because it's really hard to, given a matroid, it's really not obvious at all to come up with a list of all matroids that contain that. Especially if you're not just looking at circuit hyperplanes. It's when you have to like go up by multiple I'm not sure if there is a good method of getting a list of all such things. If there is such method, then I guess it might be possible. But if there is no such method at all, then I think it's going to be very unlikely that you'll be able to do.
Thank you.